Recording, and I've got audio. So, right out of the gate, you got any questions from the homework? What's number 5? Superman must stop a 120 kilometer per hour train in 150 meters to keep it from hitting a stalled car on the tracks. If the train's mass is 3.6 times 10 to the 5 kilograms, how much force must he exert? Compute the weight, or compare the weight of the train to the force, apparently. All right, so velocity of the train is, what was that, 150 kilometers per hour? 120. All right, start off, let's convert that to meters per second. So we've got 1,000 meters per kilometer. And we have that's per hour, so that's 1 hour for 3,600 seconds. Somebody with a calculator. Or better yet, everybody with a calculator. Anybody get anything different? Everybody get the same? All right, that's the velocity of this train. The mass of the train is 3.6 times 10 to the 5 kilograms. That's what, 360,000 kilograms? Okay. How much force does he have to exert? We need a stopping distance, delta x. (150 meters). Did I get that right? Yes. Okay, well, first we need to know how much acceleration is required to stop a train in 150 meters. Which kinematic equation are we going to use? Logan. Wait, was it you that asked about number 5 or you? Luke. Luke, which equation should we use? Tyler, welcome. Willkommen. Bienvenue. I think he just likes getting his name recorded on the video for posterity. And I bet Luke is now thinking that he's dodged a bullet and I'm not waiting for him to answer the question anymore. No. That is certainly the most general purpose of the kinematic equations. But do we know how long he's got to how long it's going to take him to stop the train. We know T. We don't know A. So that would give us two unknowns, and we would need two equations. How about we use the third one? The third one on my list. How about we use v sub x squared is equal to v sub naught x squared plus 2a sub x delta x, which is probably written as x minus x sub naught in your book. That, the only thing we don't know, we know delta x, we do not know the acceleration. We know what the final velocity needs to be, 0 meters squared per second squared. That's velocity, the final velocity will be 0. We know its initial velocity, 33.3 meters per second squared plus 2 times a sub x times 150 meters. Now let's clear something up here because that 3 bar looks like a 3 to the minus 2. So what's 33.3 squared? Let's get that out of there real quick. 1,108. Round that to 0.9 will be close enough for now. Meters squared per second squared. It's equal to 0 meters squared per second squared. And then we add to that 2 times a sub x, which is meters per second squared, times 150 meters. Now all we got to do is solve for a sub x. So we subtract the 1108.9 from both sides, and we get minus 1108.9 meters squared per second squared is equal to 2 times a sub x meters per second squared times 150 meters. Double checking our units, we've got meters per second squared times meters gives us meters squared per second squared, so we're good. Divide both sides by 2 times, what's 2 times 150 would be 300. We divide both sides by 300. What's 1108.9 divided by 300? 3.69 meters per second squared, because we divided out 1 meter from the meter squared, and that gives us our acceleration in the x direction in the proper units, meters per second squared. Was that one of the questions, one of the parts of the question we were looking to answer? Or did we just have to answer that to get to the one they want? Yeah, they want to know how much force he has to exert. Oh, and I did something wrong here. If the train is moving in the positive direction, I dropped a negative sign. That's minus 3.69 meters per second squared is the acceleration he has to. Okay, well, what is the force necessary to do the acceleration? Newton's second law, force is mass times acceleration. It's 3.6 times 10 to the 5. Get that? Yep. Kilograms times minus 3.69 meters per second squared gives us say again. 1.3 times 10 to the 6 newtons. That is the first answer they're looking for. Compare that to the weight of the train. What is the weight of the train? .6 times 10 to the 5 kilograms times 9.8 meters per second squared, acceleration due to gravity. And that gives us what? Newtons is the weight of the train. So, what percentage of that weight does the force Superman has to exert on the train? What is that as a percentage of the weight of the train? It would be 1.3 times 10 to the 6 newtons divided by 3.5 times 10 to the 6 newtons equals what? 0.39? Okay, so, or 39%. Anybody getting a different answer? Is everybody getting the same answer? Because I noticed that those aren't quite the same question. Now, for the trick part of the question. How much force does the train exert on Superman? Newton's third law of motion. The same force he exerts on the train exerts on him. Which was right here. So that's A. B and C is Newton's third law. The same, or 1.3 times 10 to the 6 newtons. You'll notice I did not include the negative sign. It was not an oversight that time. What's Newton's third law say about the force? Equal and opposite. Any questions? Everybody clear on how this one was worked? What about any other problems? Any other homework problems? You got your pictures took? Everybody got all this? I either need a stronger neck or shorter boards. I can. What's 12? Oh, draw your diagram. Here's your bucket. How much weight, how much mass is in the bucket? 14 kilograms. 14.0 kilograms, right? 3 digits. Got it. And it's being lowered by a rope. What's the tension in the rope? Say it again. 163 newtons is the force of tension in the rope. So you have mass times gravity pulling down, and the force of tension pulling up. What is the force of gravity in this case? Minus 9.8 meters per second squared times 14.0 kilograms equals, you can do the calculation if you want. Negative 137 newtons. So we've got minus 137 newtons pulling down, plus 163 newtons pulling up. The vector sum of the forces is equal to the mass, 14.0 kilograms, times its net acceleration. And the vector sum of the two forces are plus 163 newtons minus 137 newtons, which is equal to, say again, 26 newtons. Everybody get the same answer? All right. 14.0 kilograms times A equals 26 newtons. Divide both sides by 14. And that's actually 26.0 newtons because we had 3 significant digits. .86 meters per second squared. Yeah, because that's not 14 newtons, that's 14 kilograms, which we divide out of the newtons, leaving meters per second squared. Is everybody getting the same answer? Okay. So the net acceleration of the bucket is plus 1.86 meters per second squared. What's the direction of the motion? Positive is up in this case. Anybody got any more questions? All right, well then let's look at chapter 4-7. Let's start talking about how you solve these three-body problems like this. Megan, willkommen. Did someone else sneak in with her, or was that just you getting up and moving around? Okay. All right. What we just learned by working that last problem, well, actually both of those problems, is that the acceleration of a body is going to be the force exerted on it divided by its mass. Or, stated differently, going back to Newton's 3 laws of motion, the second law of motion is just that. The vector sum of the forces applied to a body, to an object, will equal its mass times its acceleration. You apply the same force to something that is low mass, it will accelerate more than if you apply that force to something that is heavier, higher mass. Well, now, let's look at some examples where the vectors are not neatly arranged in equal and or in opposite along one single axis, so they're not neatly opposite one another. The first example they give in the book is a boat being pulled down a canal by 2 men walking on either side of the canal, towing it by a line. Here's the boat. And here are the banks of the canal. And you got one guy here, one guy here. Both of them are pulling on a line to drag this boat down the canal. Now this one, force of A is at an angle of what, 45.0 degrees. The second one, F sub B, is at minus 37.0 degrees. We define the horizontal as the positive x-axis. And they are 40.0 newtons and 30.0 newtons respectively. Okay, what is the vector sum of these two forces? And what's the first thing we got to do to add vectors? Convert them into their rectangular components. So, force A is equal to 40.0 newtons times the cosine of 45.0 degrees I plus 40.0 newtons times the sine of 45 degrees J. Force sub B is equal to 30.0 newtons times the cosine of minus 37 degrees I plus 30.0 newtons times the sine of minus 37.0 degrees J. All right, what's this first term here? 40 times cosine 45. 28.3 newtons I plus 40 sine 45 degrees without your calculator. 45 degrees, it's the same both ways. It's the midpoint. So it will be 28.3 newtons J. 30 times the cosine of minus 37 degrees. .95, so that would be 24.0 I plus 30 times the sine of minus 37 degrees. Minus 18.1 J. So, the net sum of these two vectors is 28.3 plus 24 is 52.3 I. Now, what's 28.3 minus 18.1? 10.2 J. That is the net force that they are pulling. Convert that back into polar coordinates. Magnitude of the net force is 52.3 squared plus 10.2 squared. Take the square root, and that gives us what? 53.3. And the theta is the inverse tangent of 10.2 divided by 52.3, which gives us, what'd you say? At 11 degrees. .3. What does that tell you? Megan, what does this tell you about how they're pulling the boat? Anybody? They're going to hit the upper bank, exactly. That the guy on the bottom needs to pull harder. Point is that this is how you have to do it when you want to find out the net force that more than one vector is applying to a freely moving body, or to any body, actually. Let's work through this conceptual design here. On page 88. Everybody turn to 88. Everybody there? The figure 420, top of page 88. It shows three examples of a free body diagram of a hockey puck sliding on frictionless ice. Which of those three images is the correct one? Which one of those diagrams is the correct diagram for the body, for this hockey puck as it's sliding across the ice? How many of you would be tempted, if you didn't read the response underneath it, how many of you would be tempted to say it looks like letter A would be correct? That the force of gravity is pulling down, the normal force is pushing up, those two cancel each other out, and that leaves the force pushing it to the right, causing the motion. That is, if that is what seems right to you, don't feel bad. That's actually a pretty intuitive response. And it's what most people intuitively think of when they think about free body motion, but it's also contrary to everything we've been learning about the laws of motion. The correct diagram would actually be the one in the middle. Remember, the law of inertia, the first law of Newton's first law of motion, is that however you state it, it basically means that the inertia of any object means it will resist any acceleration. So that if it's already moving, it will continue to move. If it's already at rest, it will stay at rest within an inertial frame. So the middle one is actually the correct. Now, if we did away with the assumption that this ice was frictionless, then the actual correct one would be C, that shows a force opposing the motion of the hockey puck. What would that tell you was actually happening? That the puck is slowing down. That it will eventually slow down and come to a stop all on its own. That force of friction between the ice and the puck is opposing the motion and therefore tending to decelerate the motion of the puck, decelerate the puck itself. Now, in a hockey rink, obviously it's going to hit the far wall and be an icing call before it actually comes to a stop on its own. And I'm guessing from the blank looks that none of you watch hockey. Okay. Well, for everyone else, an icing call is when one of your players hits the puck all the way to the other end of the rink without someone in the middle catching it first. Point is that ice is near frictionless enough that it would take a very long time for that force vector to bring that hockey puck to a stop. But in the real world, that force vector would be there. It would be real. It would be exerted by the ice on the puck, and eventually it would bring it to a stop. The puck would not just continue to slide indefinitely. But we will get to friction in a few more lectures. For now, we're still going to assume frictionless surfaces. Let's look at these. These are they give you the problem-solving strategy for dealing with free body motion or free body diagrams. First, draw a picture, draw a sketch of what's actually going on. Next, consider only one object at a time, especially when you have multiple objects that, working together, interconnected, whatever. Consider one object and only one object at a time. Look at the forces acting on that object and that object only. That means you're not concerned with the forces that it's exerting on anything else. You're only looking at the forces that are being exerted on that body. Okay, so Newton's third law, equal and opposite forces. You ignore the ones that it's exerting on any other bodies, and focus only on the forces that are actually acting on that particular body. Once you've got the vectors identified, the force vectors identified, resolve them into rectangular coordinates, if they aren't already conveniently done so, and add them together. That gives you the net force equals mass times acceleration of the object. yeah, we're going to get to friction later this week. Up till now, we've been dealing with forces and vectors that were conveniently orthogonal, perpendicular to one another, which made it easy. You know, the force normal, the gravity force were perpendicular, were vertical up and down, motion was horizontal. So let's look at a more real world. I want to say more real world, not quite fully real world yet. Small steps, right? Let's take a look at an example that would be incrementally more realistic. Got a surface. On this surface is a box. Tied to the box is a string. And you're pulling the box by that string. It looks kind of like the picture in the book. It does, doesn't it? Looks like the back of an envelope. You're pulling on the string with a force of, what did I say, 40 newtons? What does that actually mean? And this, I want to take a minute and everybody think through this with me. Pay attention, because this is kind of important for you to wrap your mind around this. You're pulling on that rope, and you're pulling it with 40 newtons. What is actually happening? You're probably tempted to say you're pulling the box with 40 newtons of tension. Okay? But in fact, you are not pulling the box. You are pulling the string and applying 40 newtons of tension to the string. The string, the tension in the string, is what's actually pulling on the box. And that may seem like a trivial distinction to make, but it will not always be so. Okay? So, the force of tension in the string is equal to the force of pulling that you are applying to the string. Okay? So the point is it's still going to be 40 newtons, but there is a subtle distinction, and it is not a distinction without a difference. It will be important, especially later on. Let's see, they say this is at 30.0 degrees. 30.0 or just 30? 30.0 degrees. Now, what other forces are acting on this box? Force of gravity is pulling down. And the normal force is pushing up. What is the normal force in this case? The force of gravity is going to be 9.8 minus 9.8 meters per second squared times mass, times the mass of the box. Do they ever give us the mass of the box, or just leave it as? They do say, yeah, 10.0 kilograms. And that makes it awfully convenient to just say it's 98 minus 98 newtons is the force of gravity. You might also be tempted to say then the normal force is also 98 newtons, but it is not. First, we've got to break this force of tension into its rectangular coordinates. So we've got 40.0 newtons times the cosine of 30 degrees, I plus 40 times the sine of 30 degrees, J. What's 40 times cosine 30? 34.2. 0.6 newtons I, and 40 times sine 30. So the vector sum of the forces in the vertical equals 20 newtons plus 20 newtons plus the normal force minus 98 newtons. So 98 newtons equals 20 newtons plus the force normal. Subtract 20 from both sides, and somebody verify that, please. Good. We've got 78 newtons is the normal force. The normal force is less in magnitude than the force due to gravity, which tells us that the box does not move in the horizontal, in the vertical. Okay? That's because the sum of the vertical forces, which includes the vertical component of the force of tension plus the force normal, is equal and opposite to the force of gravity. So it doesn't move. That leaves the vector sum of the horizontal forces is just the horizontal component of the force of tension, which is 34.6 newtons I. And then we solved that for its acceleration. That's equal to its mass times its acceleration. Mass is 10 kilograms, so you divide both sides by 10. You get 3.46 meters per second squared is the acceleration that the box will experience horizontally. Everybody see how that was done? Seriously, anybody have any questions about how we solved this? How we analyzed it? Okay, then let's revisit a problem very similar to the last lab we did. Got all your pictures, everybody? We did the lab on dynamics. We had one mass suspended over a pulley, pulling on a much heavier mass horizontally. In this case, let's analyze this one just as two boxes, both on the same horizontal surface. How are they labeled? Mass B is 12 kilograms. And mass A is 10 kilograms. And you are pulling on it of 40.0 newtons. Perfectly horizontally. So, right out of the gate, we don't have to worry about converting anything into rectangular coordinates because everything's already horizontal or vertical. Now, first let me point out to you that it would be perfectly legitimate to treat this entire arrangement as a single object of 10 plus 12 is what, 22 kilograms that you are pulling on with a force of 40 newtons. Okay? And if you did that, you would solve it and get the right answer for how much acceleration it's going to experience. But that is not physically what's going on. You could treat it that way because then this force of tension of this string between the two boxes simply becomes an internal force. And the force of tension pulling this way would equal the force of tension pulling that way. They would cancel each other out as an internal force. And your result would be the same. But what's actually happening here, you are pulling on the string with 40 newtons of force. That means you are putting 40 newtons of tension in this string. That string is what is pulling on mass A with 40 newtons of tension. Okay? You are not pulling on the box. You're pulling the string. The string is pulling the box. We've also got the force of gravity and the normal force. They're canceling each other out. So we're just going to ignore those. We're not worried about, we're not having to resolve any additional forces to come up with any vertical calculations. We're strictly looking at the acceleration of the boxes on the horizontal plane. So, there is also a force of tension here, which means I'm going to change that to just force 1. Okay, so as not to confuse it with the tension in this string. We'll call force of tension 2. Right? The force of tension in this string is pulling backwards on this box and forward on that box. Okay? But what's the first rule we talked about? Analyzing free body motion diagrams. Treat one object at a time. So we look at only this object. What are the vector sum of the forces? Plus the vector sum of the forces in the horizontal R plus 40.0 newtons minus force of tension 2. And that equals mass A times acceleration of A in the horizontal. Acceleration A sub x. Now, what forces are acting on this box? Again, we've got gravity and the normal force that cancel each other out, and that leaves just the force of tension 2 acting on this box. because again, we're ignoring friction. That's equal to mass B times the acceleration of B in the x direction. And I've done this on purpose. We have two different accelerations here. The acceleration of mass A and the acceleration of mass B. However, because they are connected by this string that remains taut and does not stretch, whatever acceleration this body experiences, this one must experience the same. They're connected, and as long as the string stays taut and doesn't stretch, if one accelerates, they both have to accelerate. So, we can rewrite both of these as 40.0 newtons minus Ft2 is equal to mass A times acceleration, and Ft2 is equal to mass B times acceleration. Any questions how we've gotten to this point? Everybody see what's going on? Well, we have a separate equation right here for force. The force of tension 2 is equal to mass B times acceleration in x. We substitute this in here. What do we have? 40.0 newtons equals ma times the acceleration of x plus mb times the acceleration of x. We factor out the acceleration of x, and we end up with mass A plus mass B, which, if you'll recall, is what I told you would happen. I told you we could just treat these as one individual unit. That you are pulling as one object, as just the sum of the masses, and that this internal tension would just be an internal force that you don't have to worry about. That's exactly what we wound up with. The force equals the mass times the acceleration. The point of the exercise is to get you thinking in terms of how what's actually happening, in the physics of what's going on. You're not just pulling two boxes, you're pulling a string. A string is then pulling the first box, which pulls another string, which pulls the second box. And it's when you really do need to know how to break down these forces and apply the correct forces to the correct bodies in the correct way in order to solve these problems. And we're out of time, so we'll pick up here next on Wednesday with an Atwood machine, where things start getting a little more complicated.